All right, mercifully, we're at the last video of this section, and we've got two examples left of indeterminate products to do. So let's look at this one. X is going to infinity, and we've got this, which is going to infinity, raised to this, which is going to 0. So this is an infinity to the 0 type. And so what this means is we could get really any possible number from this sort of type. So we'll treat this the same way as we did the others. We'll let y equal e to the x plus x raised to the 1 over x. We'll take the ln of both sides of this, and then we will use the power rule for logarithms to rewrite this as 1 over x ln of e to the x plus x. All right. So let's see. Now we'll take the limit of this. The limit as x goes to infinity of ln of e to the x plus x over x. And let's see, what can we do with this? Let's see, we've got a natural log on top and an x on bottom, but because this is natural log of e to the x up here, and not just natural log of x, we can't just jump straight to the answer and say this is, if this e to the x weren't here and that were just an x on top, then by the fact that logs are slower than polynomials, that would give us 0. But we can't do that because of the e to the x. So what I want to do is just use L'Hopital's rule here. And just first off, notice the top, when x goes to infinity, this goes to infinity, and so its natural log also does. So this is an infinity over infinity. Let's take the, let's use L'Hopital's rule. All right, on top, if you take the derivative of that, we get e to the x plus x underneath e to the x plus 1. And then on the bottom, we just get 1. All right, so let's rewrite this. We've got limit as x goes to infinity of e to the x plus 1 over e to the x plus x. And there are two ways you could do this. You could just say, okay, dominant terms on top and bottom are this, and that just gives you 1. And so the answer is 1. But let's use L'Hopital's rule one more time just to show that this works. If you take the limit, if you take the derivative of the top and bottom, derivative of the top is e to the x, derivative of the bottom is e to the x. Well, e to the x plus 1, and we could do this one more time if we really wanted to. On top you get e to the x, on the bottom you get e to the x, and so that's just going to be 1. Now really we could have stopped here or here and just said the answer is 1. But the reason is, over here, when x grows large, e to the x and e to the x plus 1 are essentially going to be the same number. You get something like a jillion and 1 on the bottom and a jillion on top, then that's essentially 1. It approaches 1. So anyway, we get 1 for this, and so our answer, remember that 1 is the limit of this function here. The one without the natural log, we have to do e raised to that. So e to the 1 equals e. And we can check our answer by graphing this on Desmos. And I graphed this thing on Desmos earlier. And let's see, on this one, we're talking about what happens when x grows large. So if we move across here and we keep going further and further out, this is approaching, notice it's 2.718, it's approaching e. All right. All right, last example. Limit as x goes to 0 of cosine x to the 1 over x. All right, so let's look at this first. When x goes to 0, cosine of x, that's 1. And then up top, that's infinity. So this is a 1 to the infinity type. So let's let y equal cosine x raised to the 1 over x. We're going to take the ln of both sides. And so we get ln y is equal to 1 over x ln cosine x. So x goes to 0 of 1 over x ln cosine x. So we've managed to turn this into a, let's see, an infinity over, well, when x goes to 0, cosine goes to 1, and this is ln of 1, which is 0. So we've turned this into an infinity times 0 type. So let's see. What that means is we either want to rewrite it as limit as x goes to 0 of ln cosine x over 1 over x. Notice what's going on there. This is going downstairs. So instead of well, actually, it's a lot simpler than that. This is just this 1 over x ln cosine x. I'm just rewriting it like this, and so now we've got a 0 over, or we've got 0 on the bottom, and what do we have on top? ln of 1. Yeah, so this is a 0 over 0. We could rewrite it like that. We could also rewrite it like this. X goes to 0 of 1 over x over 1 over cosine x, but that's going to be more trouble than it's worth. I really sort of made this more trouble than it's worth. When you take this and rewrite it like this, truth is, you can just rewrite it like this, and you've got a 0 over 0. So L'Hopital's rule is going to make quick work of this. On the top, you've got, let's see, cosine down here, and derivative of cosine, which is negative sine, on top. And downstairs, derivative of x is just 1. So x goes to 0. Got minus sine x on top, cosine x on bottom. So plug in the 0, you get negative 0 over 1, which is just 0. And so my final answer is e to that, e to the 0, which is 1. And let's check that. Over here on Desmos, if we look at that graph, when x approaches 0, yeah, if we zoom in here, as x approaches 0, y is approaching 1. If we get dead on there, it's undefined. We don't care about what happens when x is equal to 0. We care about what happens when x is approaching 0. And when x approaches 0, y approaches 1. All right, that's it for L'Hopital's rule.